Okay, now in the previous two videos we basically focused on non-uniform motion. We looked at the vertical case, and what we did was we only focused on two points. We looked at the bottom, at the top, and at both these points the only acceleration that we had to deal with was the centripetal acceleration. But what happens at any other point? Okay, what if the string is making an angle theta with the vertical? So let's figure out what the forces are for this case. Okay, even in this situation, the one thing that you need to realize is you go back to your basics, which is draw the free body diagram and then allow that to give you all your information. Okay, so let's do that. So in this case, when the object is making an angle theta, here what we have is a mass moving with speed v in this direction, and it's making an angle theta with the vertical. So let's draw the free body diagram. What we have is we have mg pointing down. Okay, now we have the tension in the string at this location, which makes an angle of theta with the vertical. Okay, so these are the two forces that are acting on it. Okay, now in this case, if you look at the problem, you realize that there are going to be forces along the tangent. Okay, in fact, the only force that actually contributes to any force along the tangent is going to be the force of gravity. There's going to be a component of gravity along the tangent. We'll try to figure that out. Okay, but we also have the centripetal force, which is simply due to the fact that the object is moving in a circle, and at this instant it has a speed v. Okay, so if in this case, let's first figure out what axis we need to choose. And if you look at the accelerations, okay, what we'll have is an acceleration pointing towards the center of the circle, which is mv square over r, and we could have another acceleration, okay, along the tangent. Let's figure out what that is, once we obtain an axis. Now, since we have the accelerations that are going to be either towards the center or perpendicular to it, okay, the axis that we choose will be like so. So our x and y axis will be parallel with the acceleration and perpendicular with it. Okay, so it just makes life easy. So once we've chosen this as our axis, we realize that we need to break mg into components. Okay, and the angle theta is like so, and so the component of mg along the radius is mg cosine theta, and the one along the tangent is going to be equal to mg sine theta. Great. Now that we have this, we can write equations along the y-axis and along the x-axis. Okay, along the y-axis, my equation is going to be t minus mg cosine theta equals mv square over r. Okay, and the equation along the x-axis is going to be equal to, if you look at mg sine theta, it is pointing along the negative x-axis. So as the object is going up, okay, this tangential force, okay, mg sine theta, okay, is equal to ma sub t. So in this direction right now, it's negative mg sine theta, simply because it's pointing along the negative x direction. Okay, and this equation actually for the tangential force ends up giving us that the tangential acceleration is going to be equal to negative g times sine theta. Okay, and it makes sense, because if you look at this g sine theta is acting in the direction opposite the velocity, so it is basically slowing it down, and that's what we expect. As it's going up, we expect the object to slow down. Okay, and the second equation here, of course, it gives us t minus mg cosine theta equals mv square over r. And if you want to check, you can see that for the vertical cases, when it's at the bottom or when it's at the top, this equation, this second equation for the t minus mg cosine theta equals mv square over r, it reduces to the two equations that we had for the bottom and for the top. Okay, at the bottom the angle theta is 0, so we get t minus mg. Well, cosine of 0 is 1, so we get t minus mg equals mv square over r. Okay, which is exactly what we had at the bottom. And at the top of the arc, the theta is 180 degrees, and so that gives us t plus mg equals mv square over r, because cosine of 180 is minus 1. So this satisfies all the conditions of the previous things, but it also tells us that, hey, at any other angle, the object is going to have a tangential acceleration, and that tangential acceleration is going to be equal to g times sine theta. Okay, having said that, let's just look at one simple case here. What happens when the object, when the string, or whether it's moving in this, it could be a string, or whether it's a card along the roller coaster, when it is oriented like so. So in this case, actually the problem is very simple. If you were to draw a free body diagram, you would have T going to the left, you would have mg pointing down, and now you would have a centripetal acceleration of mv square over r. Let's say it's some speed v at this point. It's moving with some speed. Let me use a different color so that you realize that it's not a force, it is just my speed that is at this point. So it's moving at this point with speed v. And what we can do is, now we can write down our equation saying that T is simply equal to mv square over r, and mg is equal to m a sub t, or negative mg is a sub c. So a sub t is equal to negative g, which is what is expected. At this point, you see all of gravity is trying to slow it down, not just a component. And so the acceleration, instantaneous acceleration only, keep that in mind. It's not fixed anymore. The acceleration is continuously changing. So we can figure out the acceleration at that point, the tangential as well as the centripetal, given all these conditions.